Tomaso Poggio, who will address what I think is one of the big mysteries in deep convolutional neural networks, why and how they work given the enormous amount of parameters that they have. So without further ado, Tommy.
Thank you, Gabriel. So I plan to speak today for an hour about theoretical issues in deep networks. It's not clear whether this has much to do with the brain, because it's really an open question whether deep learning of today is something that the brains really implement. Probably not. But deep learning today has this theoretical puzzle in front of theoretician. We still don't know why it works as well as it does. And so in understanding why this happens, we can expect much better future learning machines. Maybe not of a deep learning type, but growing from our understanding of how learning works. The analogy, the metaphor, the historical parallel I'd like to mention is a bit grand, but is electricity. Alessandro Volta discovered electricity, basically, how to produce it for more than a microseconds. He discovered the pila, the battery. This was at the end of 1700, and it was made a count by Napoleon for that. And once scientists had a way to study electricity over a longer time than just sparks and lightning, there were a number of practical applications, even if they did not understand really what electricity was. Applications such as the telegraph, the electrical motor, the electrical generators, electrical lights and lightning. And, but it was only until Maxwell appeared with his theory of electromagnetism 60 or 70 years later, that real big progress ground on electricity started. It was the radio, was the television, was in the radar, was computers, was the internet, was deep learning of today. So theory can be powerful, and that's why we are trying to solve this puzzle, the theory of deep networks. So let me remind to all of you what the basic computation is. You have a series of layers. As we mentioned, they started from Huber and Wiesel's suggestion of a hierarchy of simple and complex and hypercomplex cells. And this processing of information in the deep layer goes through these stages in which the weighted sum of activities from units in the previous layers is passed through a rectified non-linearity, which then outputs one number, which is 0 if this weighted sum was less or equal to 0, and is the weighted sum otherwise. That's it. And you repeat that for all units and for all layers. You set the weights using backpropagation gradient, essentially gradient descent or stochastic gradient descent. I'll come back to that later, but this is the basic architecture. So there are a number of questions that one can ask, and I'll group them in three different topics. This is somewhat arbitrary, but one question is, about approximation theory. Forget about learning for now. Just ask a very specific question. Why are deep networks better than shallow network with just one layers and one layer of trainable weights? And then there are questions about optimization. How do I train the networks with gradient descent? And about generalization. Why can network which have more parameters than data points, more parameters than the size of the training set, can generalize to new examples, so predict well. Okay, so let me start with approximation theory, where the situation is a bit more clear. And since the 80s, we know that shallow networks on the left and deep networks on the right can both approximate essentially with arbitrary accuracy any nonlinear functions between, say, the inputs, D inputs, and one output. So they are universal approximators in principle, but they also are subject to what is called the curse of dimensionality, which is that the number of parameters you need in order to perform this approximation is in the order, this is an upper bound, in the order of epsilon to the minus d, where d is the number of inputs if you want. In this example here is 8, and epsilon is the accuracy that you want. And so for instance, epsilon is 10% and d is 10, you have a number of parameters that can be as high as 10 to the 10. And of course, if the dimensionality of the input is not 10, but say 1,000, then this number, this upper bound, becomes really, really large. However, if we want to ask why are some deep networks, well, let me phrase it again. Are there some functions, some classes of functions for which deep networks are better than shallow networks? And one answer is that for functions that have the structure given in the example above, they are functions of functions of functions, like G3, a function of G21, which is a function of G11, and so on, and the dimensionality of the constituent functions, the G11, G12, and so on, is small, then deep networks can beat the curse of dimensionality, where shallow networks don't. This is essentially exploiting prior information that you have or may have about the structure of the function, that is, can be represented in this hierarchical compositional way. So essentially, for certain classes of input-output mappings that can have this representation, then deep networks with the same kind of graph structure can beat the curse of dimensionality. Shallow networks cannot. And this network that can do that are essentially convolutional networks, or the class defined by the theorem is a bit more general than convolutional network. It includes convolutional networks that do not have weight sharing. Because it turns out that weight sharing can decrease the complexity, the number of parameters you need, but not exponentially, where the locality of the constituent function, the low dimensionality of the constituent function, does beat the exponential curse of dimensionality. Okay, the proof is simple, and essentially based on checking that if you have an approximation error in the first layer, for the first layer of constituent function, this will not grow in the second and other layers. Um, there are papers, I pointed to one of them in one of the slides, and we can check empirically that this is what happens both for the training and the test error. And this is CIFAR 10, experiments done by Chen Liao, one of my great students. And you can see that on CIFAR 10, shallow networks do the worst, and deep, dense network are next, and then convolutional networks without weight sharing are next, and then close by are convolutional networks with weight sharing, which are the best one in terms of both training and test error. One can ask why convolutional network plays such a big role, and then these results, I recall the big success stories of deep networks like ImageNet and similar applications in text and speech are using convolutional networks. So convolutional networks are really the ones providing the big wins, and this is what our theoretical results in approximation would predict if, assuming that the mapping they have to approximate when you classify an image or recognize a piece of text are mappings that have this hierarchical local structure, can have this hierarchical local structure. And so why is that? In so many interesting problems, it's a kind of philosophical question. I don't want to go into that, but these are interesting open questions. Okay, so let me go next to the question of optimization. And I'm asking a specific question here, which is where is complexity control hidden in training deep networks? Now, let me recall what is done typically in training deep networks. You are trying to optimize the weights. You are trying to find weights that minimize the error on the training set. And you do this using a variation of gradient descent in which you use a subset chosen randomly of the training data at each iteration of gradient descent instead of using the whole set of training data. This is called stochastic gradient descent. Okay, and originally and so far the most successful deep networks have been used for classification, multi-class classification in the case of ImageNet and other databases, and so they're using what are called exponential type loss function, like the cross entropy typically. Now, in the binary case, a simplified version of this is the exponential loss. And so the exponential loss makes you pay a price which depends on the product of the label, which is +1 or -1, yn, and the output of your function. Of course, if the output of your function is positive, then in this loss function you pay a small price because you have the exponent of minus the product of yn f n, and but if the sign is wrong, then you pay a much larger price. And you are doing gradient descent on this, or stochastic gradient descent, and so the weights, say, of the weight ij in the matrix of weights at layer k changes the time derivative of it at this iteration of gradient descent as the expression given here. Okay, so this is going on, and I want to remind you that the puzzle is that you have, these are empirical findings that you can get zero training error if you have enough weights, enough parameters. You have zero training error, and you have a test error, which is pretty good and does not get worse as you increase the number of parameters. So you can get overfitting. You fit all the training set, very low exponential loss, very, very low, and you still predict well. So this seems a puzzle from the point of view of classical machine learning. If you think about what learning is, supervised learning like this is try to learn a function from a set of input-output data, but you want to learn a function that not only can reproduce the data, but can also predict well future data that you have not seen in the training set. And there has been a lot of work over the last 3 or 4 decades on which conditions are necessary for from learning functions that can predict, learning function from data in a way that can predict. Just to remind you of basic framework that you'll see later on next week, especially with Lorenzo Rosasco, but the classical framework for supervised learning is to think about an unknown probability distribution on XY, and to assume that you have training data that are given to you and they are drawn randomly, IID, from this unknown distribution mu. If you were to know mu, the problem would be solved, but you don't know mu. You have only some random data from the underlying distribution. So you're trying to find, to have an algorithm that can learn a map such that from the data to a space of function, so that the function that you get from training on your training set S is predictive. What does that mean? Well, we have to define a few things. One is the expected error. This is the true error, the one that you'd like to be able to compute, but you don't, because it requires the knowledge of the distribution mu. If you know that, you could compute the probability for a given input, for a given x of y, and so it is really being able to compute the probability of a future error. What you can compute is in fact empirical error, which is an error over your training set. Now, the natural idea is to find condition under which this error on the training set is a good proxy for the error you cannot compute, the expected error. And so this is what is called the distribution independent generalization, or more precisely, you can speak of a generalization gap going to 0. This is the requirement that your algorithm is so that your empirical error is a good proxy for your expected error, in the sense that it will converge to it for number of data, training data going to infinity. Okay, turns out that a necessary condition for this to happen is to constrain the space of function over which you're optimizing. And the most general condition is that the space of function over which you are looking for the minimizer of the empirical error has to have this property to be a space of function which is uniformly, Glivenko can tell you. But basically you need a constraint, like a constraint, for instance, of smoothness. It's more than you need, or compactness for the space of H. Now, so one of the messages from the work on learning theory by Vladimir Vapnik and others like Steve Smaley is that you need to control the complexity of the predictors in an implicit or explicit way if you want to predict well. Otherwise, fitting your training set will not give you a good predictor. All right. Just a note that just counting the parameters is not a good way to constrain your predictor. So it turns out that the norm of the weights and related quantities like the Rademacher complexity of the hypothesis space are the quantities that really matter. And control of the norm, of course, can be done and is what is done via regularization. So typically in a regularization algorithm, for instance, the ones used with shallow networks of the kernel machine type, what you are doing, you are minimizing the empirical error on the training set, the first term on the left, but with a constraint. You're minimizing at the same time, there is a constraint on the complexity of F, which is given by the norm in the reproducing kernel Hilbert space. Typically, this is a constraint of smoothness on the functions that you have, smoothness or norm in the, of the weights in that space. So I want to point out here, because I will come to that later, that there are some equivalence under quotation mark between Tikhonov regularization, which is what we see here. You're minimizing a loss function under with a regularization term controlled by lambda, and what is called Ivanov regularization, that is minimizing the loss. So this will be the empirical loss, subject to a constraint on for the complexity of the W. For instance, the L2 norm of the W being within a ball constrained by delta. And Morozov regularization, in a sense, the dual version of Ivanov, in which you are now minimizing the norm, for instance, subject to the constraints. And the equivalence has to be taken with care. For instance, in the Ivanov-Tikhonov case, it means that for every solution given a training set and lambda of the Tikhonov problem, if there is one, then there is a corresponding delta that gives you the same solution in the Ivanov case for the same data set. Okay, but if we come back to our problem here with deep network, we see that we have minimization of L But there is no obvious constraint here. There is no obvious constraint on the norm of the parameters or on L. It's nothing that is explicit here. So that's the puzzle. If there is a constraint, where is it? And if there is not, how can this work and produce functions that are predictive? Okay, question is, are deep nets so different that we have to throw away all of the classical machine learning theory? All right, so what is the solution? So in order to go there, let me define a couple of things. It's back to our diagram there. Now, the function that the network outputs will depend on the X input, of course, but also on the weight matrices at the different layers. 1 to K over the last, in which the last layer may be a matrix with one row only, if the output is just one output. As I said, we are considering mainly here, for simplicity, binary classification. Okay, the important thing is that if you have RLUs, then there is the following important property, which is homogeneity of a certain type. In other words, you can multiply the weights in one layer by a certain number, scalar, alpha, and the output of the function will be multiplied by alpha. This can be, gives also this property that the function of the network with the weight W is the same as rho multiplied the output of a normalized networks, where rho is the product of the Frobenius norms of the K weight matrices, and the normalized network, F tilde, is a network where all the weight matrices are normalized to have Frobenius norm 1. Now, notice that from the point of view of binary classification, what matters is really the sign of F tilde, because this would be the same as the sign of F, since F is rho times F tilde. In a lot of what I'm going to say, I'm also making the hypothesis that at some point during gradient descent, we have separability. In other words, there is a gradient descent have found a set of weights such that the sign of the network is correct. You have classification, correct classification for all the training point. As I've shown you, this is relatively easy to achieve in for data set like CIFAR. And, but this by itself, of course, does not tell us anything about testing error. So we're just assuming that optimization can do that. And the reason we can assume that is because there are a lot of parameters, so that we assume there is enough over parameterization that gradient descent can find a set of weights that can classify correctly the training set. Okay. So that's what we're going to consider. And I want to go through two different approaches. The first one, it's a new one. Don't think it's been really published yet, although it's in one of our memos, implicit. It's short, I'll give you just an outline. this basically says, forget about the dynamics for the moment and consider the following theorem, which is a theorem that is a variation of something proved a few years ago by Tibishirani and Rousset. And this says that if we minimize the exponential loss, then we are maximizing the margin. And this means that we are maximizing the value of f of xn so that xn is in this is the value, the training set that gives you the smallest separability, so the smallest value of f of xn, and you are maximizing that value, the margin. If we do minimizing the exponential loss with this expression in which we have rho and fv, where fv is the function with the normalized weights. So essentially minimizing exponential loss maximizes the margin. Then we have another result that says that maximizing the margin subject to the condition of normalization on the weights is equivalent to minimizing the weights subject to margin greater than or equal to 1. So minimum norm solution are equivalent to maximum margin solution. And then we can use a lemma in constrained optimization that says that if you are minimizing the norm subject to a number of conditions, then the optimal set of V is given by a linear combination of the df dvk over, and these are the ones that are the support vector. They are on the margin where the fvxi is equal 1. And so, and then there are other arguments you can use to say that if the weights only depends on a subset of the training points, then you can bound what is called stability. I'll come back to that later, and that bounds the test error. So that's one way, and that essentially says that if your data set is good enough, then you can bound the test error despite the fact that your training error can be 0 and so on and so forth, and despite the fact you don't have a constraint because you're using the exponential loss. The second approach, which is more direct, consider the dynamics, and let me walk you through it. In this case, as I said, the question is not whether the W converge. In fact, if you look at the equation, they will diverge, because if you assume separation has been achieved, then everything is positive, so that the gradient of W, in fact, the time derivative of W is positive. So W is growing. It's growing to infinity. The question is whether you have convergence of the normalized weight. These are the ones that matter. You can think of running gradient descent, getting some W, at some point you stop gradient descent, the W will be very large, you divide by the norm, that's what matters. You don't need to divide by the norm, you can just look at the sign, but say, you can divide by the norm, and the question is whether this will converge. And so if you change variables, essentially, in the set of differential equations that gradient descent gives you for the W, I can express W as WK is a matrix in terms of rho K VK, VK equal 1. And then if I do the kind of bothersome linear algebra that is needed, I get this equation equivalent to the one of W, but now in these two variables, the rho and the V. And the rho and the V. And I can see that rho will go to indeed to infinity. The derivative of rho goes is positive after separation, and at some point to go to 0 for time going to infinity. And the question is whether you have a V that converges. And in fact, it turns out that there are critical points of V. They will maximize margin. And in fact, you can see from this expression here that the V will have the worst, the lowest value of f of xn. So that the xn for which fv will have the lowest value. So in a sense, your classifier is less sure. Those are the ones that will have the large value as rho grows, as time goes to infinity, rho grows, and the exponential term increasingly go to 0. So the terms that have large value of f of xn, the xn terms, will go to 0 first. These are the ones that are not support vectors. They don't matter. And in the limit of infinite time, there is one group of surviving, let's call it support vectors, training points with the same margin, and they satisfy this equation. Okay, so that's interesting, and you convert to a maximum margin, and that's good. And there is also this observation, which is even more direct, which is that if I considered this loss, but now I impose a constraint on the VK. So this is really like regularization. I do that with a Lagrange multiplier. So the condition is that VK is 1 at all time, not only the convergence. And then I get equations that in rho dot and V dot, they contain lambda essentially, but I can replace with lambda with an explicit value because I have this condition on lambda. And if you see there, I imposing V transpose phi equal 1, VK transpose VK equal 1, this gives me an expression for lambda, which I substitute in the equation. And so, what happens is that I get equations that are very similar to the ones I got before without imposing this regularization. There is a rho k squared different in the equation for the V dot, which means dynamic is somewhat different from the ones without it. In fact, the dynamic obtained in this way is exactly the same that you get if you use an algorithm which was proposed as weight normalization, which is used, and it's a bit similar to batch normalization, which is used a lot. They have an implicit normalization of the weights, as in what we did here. And more importantly, the critical points I get are the same as the one I get without any normalization at all. So these are critical points at infinity, but they are the ones that determine convergent to the maximum margin solution. So interestingly, there is an implicit constraint in doing gradient descent on deep networks using exponential loss, using the exponential loss. So that's important. And so there is you get this same critical point that you will get with an implicit vanishing regularization. You get a maximum margin, minimum norm solution. And this essentially, in my view, explains why deep networks generalize as well as they do. You have to add a few comments to complete, to make my statement airtight. I'm not going to go through it, but I'll make a few comments. One is that you can characterize a number of properties of your dynamics, which are quite interesting. For instance, the rate of change is the same for all layers, is independent of K. This means if you start with weight layers, weight matrices that have the same norm at initialization, and then you just do gradient descent, then the norm should remain the same for every layer. And the way you prove that is very simple. You just take the time derivative of rho k is 2 rho k dot rho k, time derivative of rho k, and this, we found it before, was rho over rho k for something else, and so the rho k disappears, and now we have that the time derivative of rho square k depends on rho and so on, but not on rho k. So it's independent of k. Quite interesting. The margin is not decreasing for large times, only can increase. We can find things about rate of convergence for linear networks. We can show experimentally that this happens. This is work with Fernanda, a great student, and Andy Burbarsky, and you can see how the margin evolves across perturbation at different times. You can see, for instance, that is quite interesting how the margin behaves for CIFAR, natural labels, and CIFAR labeled randomly. There was this interesting paper. One of the authors was a student of mine who did the work as a summer intern at Google, showing that you can, that gradient descent and the deep convolutional networks, 5 layers, can fit exactly the training points, so separate them, zero classification error, even when they are labeled randomly. So you expect in this case that the test error would be 90%, because there were 10 classes, and you have obviously to expect random predictions. And so from the point of view of the training error, you don't see any difference between the training error on randomly labeled CIFAR data and the training error on correctly labeled CIFAR data. But if you look at the margin, you can see that the margin for the randomly labeled trained data is very small, and is small for all data points, essentially, all of the 50,000 training data. Whereas in the case of naturally labeled data, you have a margin that is pretty significantly much higher, several orders of magnitudes, for the worst point, so to speak, but then is also getting better and better for all other points. Let me focus on this results that you are maximizing the margin here using exponential loss, even without explicit normalization regularization. Okay, Now, there are a number of caveats here, and maybe I should conclude this and have enough time for questions here. But so let me make clear what the caveats are. What I assumed in the so far is vanilla gradient descent. So no momentum, no weight normalization, no batch normalization, no regularization, no data augmentation. Of course, people use all of this and more in practice, and each one of them will give you regularization, essentially, or some similar effect. So I'm taking the worst case. And by the way, that's important because if you look at results like recently about square loss behaving as well as exponential loss for classification, this work done by Misha Belkin, a student of his, they find pretty much the same result, but they are using algorithms that have all of this batch normalization and ResNet and possibly data augmentation. So, so to be taken with a grain of salt. This is what the next point makes. It says, all I told you assumes exponential loss. Open question is the same for the square loss. In terms of maximizing margin, I don't think so. Some other mechanism may be there to control complexity, but it's not the exponential mechanism. Another point is that what I told you is that gradient descent and stochastic gradient descent converge towards a minimum norm solution. But in the case of deep networks, nonlinear deep networks or multi-layer deep networks, this is in general not unique. So there are many minimum norm solutions, and some may have better test error than others. That's an open question. So, you know, it's unclear exactly what you can say about the best you can do from the point of view of generalization. Are there some other criteria than minimum norm that tells you really what is the unique best you can do? And then the other question that I was asking, because I wanted to introduce some other slides, was whether we can generalize what I said in a way that includes the classical theory and the classical approaches for kernel machines. And there is a way to do that. It's a kind of research program based on the idea of cross-validation stability as a general criteria that you can use for different situations. The traditional classical ones in which you typically have for a number of data going to infinity, you have an under-parameterized situation, but you can also apply in the modern regime in which you could consider over-parameterization also for n going to infinity. Stability gives you a criteria that you can use for a theory in both the situation, whereas you can use the standard approach of uniform convergence that requires a fixed hypothesis space. Okay, let me finish here saying that I think we are on we're making progress on understanding why deep learning works, but there is, of course, much more fun to be had in future work on these puzzles. Thank you.
Great, thank you, Tommy. We have a few questions for you. Here's one from Savia. If regularization is interpreted as the log prior when minimizing the negative log posterior, could you please give some intuition for the equivalent terms in Ivanov regularizations?
Well, the classical, let me address just the classical regularization, you can have a Bayesian interpretation for that, and this essentially is considering Gaussian priors on the function space, and so your priors is to maximize the probability of functioning in that, and if you can look at and whereas the loss term is essentially taking into account is a likelihood term taking into account additive Gaussian noise. This is kind of the Bayesian interpretation of classical generalization. It has basic theoretical issues in terms of making it rigorous because we are dealing with infinite dimensional spaces in principle, and so some of this probability and measure become quite touchy, but there is this Bayesian interpretation, yes.
Great, thanks. The next one is from Sreya Banerjee. Does the hypothesis of separability signify we have reached the global minima? And she has a follow-up of how does the theory hold for L1, L2 losses, which are commonly used for most reconstruction problems? And by theory, she means maximum margin, minimum norm.
So the separability does not correspond to the global minimum. In the case of the exponential loss, you need more than separability. And in fact, this corresponds to the fact that you can get separability, you can continue to do gradient descent. The training error in terms of classification error does not change because it was already 0, but you converge to better and better solutions in terms of test error. So for the exponential, so separability does not correspond to the absolute minimum. No. The 0 loss minimum for the case of exponential type losses happens only at infinity, so you never have it for finite times. For the square loss, the situation is of course different. You can have separability also without having 0 square loss. You have 0 square loss when you have exact interpolation. In the binary classification case, you have exact interpolation of the labels +1 and -1. But you can have separability. It's much easier to have than exact interpolation.
Great, thank you. The next one is from Roman Barval. So could you map in any way similar to universality classes in critically or something like that, or in criticality or something like that, constrained and unconstrained learning?
Sorry, can you repeat the question?
Sure. So could you map in any way similar to universality classes in criticality or something like that, constrained and unconstrained learning?
Yeah, I'm not sure what criticality classes here mean. Yeah, let's postpone this question to. I'll try to do it. Per email if the person who asked this question wants an answer.
Sure thing. Roman, if you can follow up with Tommy, that would be great. So the next one we have is from Giambattista Parascandolo. The brain has about 100 trillion parameters, but generalizes very well to lots of tasks we care about. So the bounds from learning theory seem to be irrelevant there. why should we be surprised that DNNs that have much fewer parameters generalize well?
Well, from the point of view of statistics, it's already quite surprising that you can have a system that has more parameters than data predict well. When I was starting to learn physics, one of the key concepts that was drilled in my brain was if you have a model of some physical system and you have say 10 parameters in that model, you better get at least 10 measurements, but really 20 is the minimum, and 50 would be much better if you want to fit 10 parameters. Otherwise, you're playing games. Think about a set of linear equations, and now you have more unknowns in the equations than equations. There is, of course, an infinite number of solutions that solve the equations exactly. Which one do you choose? You want one that will predict well. Which one do you choose? That's a big question. There are ways to do it. Regularization is one, but deep networks on surface seem not to do any regularization or being able to do well without regularization. So what's happening? So that's a puzzle.
Great. And we have time, I think, for one more. Another from Giambattista that got voted up. Do you think it makes sense to think of DNNs as massive ensembles of subnetworks in the regime of reasonable data? Each subnetwork then has reasonably few parameters, and the contradiction would disappear?
Well, the contradiction, as I said, does not disappear. Again, I want to stress again, in reality, it's not the number of parameters but constraints of the complexity, such as constraints on the norm. But what you say is the burden of the proof is on you, is that by having this decomposition that you suggest, you get somehow some constraint on how these networks are combined together, their coefficient, for instance. If you can do that, that would be great. That would be a nice result. I don't see how this can be done, but please send me an email if you manage.